Welcome to this walkthrough of LeetCode problem number 755, Poor Water. Today, we'll explore how to simulate the behavior of water as it interacts with a terrain represented by an elevation array. This is a fascinating problem that combines elements of simulation and array manipulation. Let's dive in. In this problem, we are given an elevation map represented as an integer array called heights. Each element in this array corresponds to the height of the terrain at that specific index. Along with this, we are provided two additional parameters: volume, which represents the total amount of water we need to pour, and k, the index where the water starts being poured. Now, the task is to simulate pouring all the water onto the terrain at index k, following a set of specific rules. First, the water tries to flow to the left, looking for the nearest position with a lower height than its current location. If it finds multiple valid positions, it will settle at the leftmost one. If it doesn't find any suitable position to the left, the water then attempts to flow to the right, again searching for the nearest lower height. If multiple options exist, it will settle at the rightmost valid position. Finally, if the water can't move either left or right, it will simply settle at index k. This process is repeated for each unit of water until the entire volume has been poured. The goal is to return the modified terrain heights after all the water has been poured according to these rules. Let's look at the first example to understand how this works. Here, the elevation map is represented by the array 2, 1, 1, 2, 1, 2, 2. The total volume of water is 4, and the starting index for pouring water is 3. Initially, the terrain at index 3 has a height of 2. When the first unit of water is poured at index 3, it checks to the left and finds that index 2 has a lower height, so the water moves to index 2 and settles there. The updated heights array becomes 2, 1, 2, 2, 1, 2, 2. Next, the second unit of water is poured at index 3. This time, the water moves further left to index 1, which is the first lower height to the left of index 2. After settling at index 1, the heights array is updated to 2, 2, 2, 2, 1, 2, 2. For the third unit of water, when poured at index 3, there are no lower heights available to the left. So, the water checks to the right and finds that index 4 has a lower height. The water moves to index 4 and settles there, updating the heights array to 2, 2, 2, 3, 2, 2, 2. Finally, for the fourth unit of water, there are no lower heights to either the left or the right of index 3. As a result, the water settles at index 3 itself, and the final heights array becomes 2, 2, 2, 3, 2, 2, 2. This example demonstrates how the water flows and settles based on the rules, one unit at a time. In the second example, the terrain is represented by the array 1, 2, 3, 4, the volume of water is 2, and the water starts pouring at index 2. When the first unit of water is poured, it moves left to index 1, as that is the first lower height compared to index 2. After settling there, the heights array becomes 1, 3, 3, 4. When the second unit of water is poured, there are no lower heights available to the left of index 2, so the water settles at index 2 itself. The final heights array becomes 1, 3, 4, 4. In the third example, we start with the terrain 3, 1, 3, a volume of 5, and the water being poured at index 1. The first unit of water settles at index 1, updating the heights to 3, 2, 3. The second unit also settles at index 1, making the heights 3, 3, 3. For the third unit, since the height at index 1 is now equal to its neighbors, the water moves left to index 0 and settles there, resulting in 4, 3, 3. The fourth unit of water moves right to index 2 and settles there, updating the heights to 4, 3, 4. Finally, the fifth unit of water settles back at index 1, as it is the next available position, and the final heights become 4, 5, 4. This example highlights how the water adapts to the terrain and fills up the lower heights systematically. Additionally, the problem comes with constraints, such as the size of the heights array ranging from 1 to 100 and the volume of water being as large as 10 to the power of 6. Special edge cases include scenarios where the volume is 0, where the terrain is flat, or where the volume is significantly large. Each of these cases ensures the solution is robust and efficient under different conditions. To tackle the poor water problem on LeetCode, we need to simulate the behavior of water as it interacts with a terrain represented by an elevation array. The water follows specific rules, settling based on the terrain's heights and moving left, right, or staying in place at the pour point. One straightforward approach to consider is the brute force method, where we simulate each unit of water step by step. Starting at the given index k, we first look to the left to identify the lowest position where water can settle. If multiple positions have the same height, the leftmost one is chosen. If no valid position exists on the left, we then check the right side. If neither direction offers a lower position, the water settles at k. This process is repeated for every unit of water. While this approach is simple to understand and implement, its complexity grows quickly with larger inputs. For each unit of water, we may traverse the entire terrain, resulting in a time complexity of O, volume *n, where n is the length of the elevation array. The brute force approach, though intuitive, has its limitations due to its inefficiency for larger inputs. To address this, we can consider an optimized simulation approach that reduces redundant checks. Instead of repeatedly traversing the terrain, we break the simulation into 3 clearly defined steps for each unit of water. First, we traverse left from k to find the lowest valid position. If no position is found, we then traverse right from k. Finally, if neither side offers a lower position, the water simply settles at k. By performing only one traversal per direction and dynamically recording the lowest position, we eliminate unnecessary computations. This approach still has a worst-case time complexity of O, volume *n, but it is significantly faster in practice due to fewer redundant checks. While this method strikes a good balance between efficiency and simplicity, we can also explore an alternative approach using a priority queue to further optimize the simulation. Using a priority queue, or min-heap, allows us to dynamically keep track of the lowest positions as water is poured, avoiding the need for repeated terrain traversals. For each unit of water, we extract the position with the minimum height, adjust its height, and update the heap. This approach reduces the time complexity to O, volume *log n, as heap operations are logarithmic in nature. However, while this is the most efficient approach for large inputs, it introduces additional complexity in terms of implementation. After evaluating the options, the optimized simulation approach with directional traversal emerged as the chosen strategy. Water's movement is limited to left, right, or staying at the pour point, which simplifies the simulation into 3 systematic steps. By avoiding unnecessary checks, this method achieves a balance between efficiency and ease of implementation. While the priority queue approach is more efficient in theory, the optimized simulation is simpler to code, debug, and understand, making it a practical choice for this problem. The optimized simulation approach provides a solution that is both efficient and straightforward. By systematically breaking down the water's movement into left, right, and settle steps, we minimize redundant computations while maintaining correctness. This strategy ensures that the terrain is updated accurately as water is poured, making it suitable for a wide range of input sizes. While it may not handle extremely large inputs as efficiently as the priority queue method, its simplicity and clarity make it an excellent choice for this problem. In this problem, we are tasked with simulating how water behaves when poured onto a terrain represented by an array of elevations. Think of the terrain as a series of columns, and our goal is to determine how the water moves and settles based on 3 specific rules. First, water always tries to flow to the left, moving toward lower elevations as long as the terrain allows. If leftward movement is blocked, the water then tries to flow to the right, again seeking lower elevations. If neither direction offers a valid path, the water settles at the current position. To achieve this, we initialize the input variables, an elevation array heights representing the terrain, a value v for the number of water units to pour, and an index k where the water starts pouring. For each unit of water, we simulate its movement and update the terrain directly in the heights array to reflect the changes as the water settles. The simulation involves sequentially applying these rules to determine where each unit of water ends up. Once the initialization is complete, the simulation begins by processing each unit of water. Starting at the pour index k, the first step is to attempt flowing left. This involves traversing backward from the current position while the elevation continues to decrease. If a lower elevation is found, we record that position as left_POS. If the leftmost valid position is indeed lower than the starting index, we settle the water at left_POS by incrementing its elevation in the heights array. At this point, the current unit of water is fully processed, and we move on to the next. However, if flowing left is not possible, we proceed to the next step, flowing to the right. Similar to the left flow, we traverse forward from the current position while the elevation decreases. We record the lowest position reached as right_POS. If this position has a lower elevation than the starting index, we settle the water at right_POS. Again, the simulation for this water unit stops here. Finally, if neither left nor right flow is valid, the water simply settles at the current position K by incrementing the elevation at that index. After all V units of water have been processed, the updated heights array is returned as the result. To implement this algorithm, we use a few key data structures and insights. The heights array itself is the primary data structure, and we update it directly to reflect changes in terrain as water settles. Additionally, variables like left_POS and right_POS are used to track the lowest positions reached during each water unit's simulation. The algorithm follows a greedy approach, always prioritizing the lowest position for water to settle, first checking the left, then the right, and finally the current position. This approach ensures that the water flows naturally according to the rules. There are also several edge cases to consider. For example, if the terrain is completely flat, water will stack at the pore index. If the pore index is at the boundary of the array, the water can only flow inward. And if all positions are higher than the pore index, the water will always settle at the pore index. In terms of efficiency, the algorithm processes each unit of water in O(n) time, where n is the length of the heights array. For V units of water, the total time complexity is O(V*n). To optimize further, we can stop checking directions as soon as a valid position is found, and since we update the heights array in place, no additional space is required. The pseudocode for this algorithm provides a clear breakdown of the steps. For each unit of water, we start at the pore index K and initialize the position as POS. First, we attempt to flow left by decrementing left_POS while the elevation decreases. If we identify a lower position on the left, we settle the water at that position by incrementing the elevation. Otherwise, we move on to the right flow. Here, we increment right_POS while the elevation decreases, and if a lower position is found, we settle the water there. If neither left nor right provides a valid option, the water settles at the current position POS. Finally, after processing all units of water, the updated heights array is returned. This pseudocode captures the core logic of the algorithm, ensuring that the water behaves according to the problem's rules while maintaining efficiency through in-place updates and early exits. To make the algorithm more concrete, let's walk through an example. Suppose the input terrain is given by heights equals 2, 1, 1, 2, 1, 2, 2, with V equals 4 units of water to pour in a pore index of K equals 3. For the first drop, we start at index 3 and attempt to flow left. The water moves to index 1, which has the lowest elevation, and settles there, updating the terrain to 2, 2, 1, 2, 1, 2, 2. For the second drop, starting again at index 3, the water flows left and settles at index 2, resulting in an updated terrain of 2, 2, 2, 2, 1, 2, 2. The third drop starts at index 3 but is blocked from flowing left, so it flows right instead, settling at index 4. The terrain becomes 2, 2, 2, 2, 2, 2, 2. Finally, the fourth drop starts at index 3, but all paths are blocked, so the water settles directly at index 3. The final terrain is 2, 2, 2, 3, 2, 2, 2. After processing all 4 units of water, the final output is 2, 2, 2, 3, 2, 2, 2. This result reflects the terrain after all water has been poured and settled according to the rules. The algorithm ensures that water flows naturally to the lowest possible position, updating the terrain in place at each step. This approach balances simplicity and efficiency, making it well suited for the problem requirements. This implementation solves LeetCode problem number 755, pour water by simulating the process of water being poured over an elevation map. The function takes the terrain heights, the amount of water to pour, and the starting index K. The algorithm iterates for each unit of water to be poured. For each unit, 1. Start at position K. 2. Move left while the elevation decreases or stays level. This ensures water flows to the leftmost viable position. 3. If the leftmost position is reached or blocked, evaluate the rightward path. Water moves right if the elevation decreases or stays level and the current position is not K. 4. After exploring the rightward path, if the water cannot stay there, e.g., a higher elevation blocks the flow, it moves back toward K if the left path is lower than the current position. 5. Once the correct position for the water is determined, increment the elevation at that position to simulate the water settling. The function returns the updated heights array after all water has been poured. This approach ensures the rules of water flow, leftward priority, then rightward, and finally the original position, are fully respected for each unit of water. The solution efficiently handles edge cases such as flat terrains or steep slopes, and it runs in O, volume asterisk n, time, where volume is the amount of water and n is the length of the heights array. Here, we start with the pour water method, which simulates the process of pouring water into an array of heights. The method takes three parameters: heights, an array representing the terrain, volume, the amount of water to pour, and k, the index where we start pouring. First, we determine the length of the array and iterate volume times, as each iteration simulates pouring 1 unit of water. We initialize a variable POS to k, representing the current position where we are evaluating where the water might settle. Now, we try to move water to the left by checking if the height to the left of the current position is less than or equal to the current height. If this condition is true, we decrement POS, moving to the left. This ensures that the water flows downhill or stays level as it looks for the lowest point. However, if no valid left position is found, we prepare to evaluate the right side. If moving left is not an option, we attempt to move the water to the right. This is done by checking if the height to the right of the current position is less than or equal to the current height, and we ensure that we are not stuck at the starting position K. If this condition is met, we increment POS, moving to the right. Now, if the right path is also not viable, meaning the water cannot settle there, we return to K by moving back leftward, ensuring that any upward slopes do not block the water from returning closer to its original position. Finally, once the best position to settle the water is found, we increment the height at that position to simulate the water being added. This process repeats for each unit of the volume. Once all the water has been poured, the updated heights array is returned, reflecting the new terrain after the simulation. To start, we're looking at a basic example where the heights array is 2, 1, 1, 2, 1, 2, 2, the volume of water to pour is 4, and the initial pour index K is 3. Initially, the heights remain unchanged, and we have 4 units of water to distribute. For the first unit of water, we begin at position 3. Moving left, we compare heights 2 with heights 3 and see that 1 equals 2, so we move to position 2. Continuing left, we compare heights 1 with heights 2 and find 1 equals 1, allowing us to move to position 1. However, we can't move further left because heights 0, heights 1. At this point, we drop the first unit of water at position 1, increasing its height to 2. The updated heights become 2, 2, 1, 2, 1, 2, 2. Next, we pour the second unit of water. Starting again at position 3, we move left to position 2 because heights 2 equals heights 3. However, we can't move further left since heights 1, heights 2. Dropping the water here at position 2 raises its height to 2, resulting in heights 2, 2, 2, 2, 1, 2, 2. Now we proceed to the third unit of water. Starting at position 3, we find that moving left isn't possible because heights 2, heights 3. Instead, we move right and compare heights 4 with heights 3. Since 1 equals 2, we move to position 4. However, we can't move further right because heights 5, heights 4. As a result, the water is dropped at position 4, increasing its height to 2. The heights now become 2, 2, 2, 2, 2, 2, 2. Finally, for the fourth unit of water, we start at position 3 again. This time, neither left nor right movement is possible because both heights 2, heights 3, and heights 4, heights 3. Consequently, the water is dropped at position 3, raising its height to 3. The final heights array is 2, 2, 2, 3, 2, 2, 2. In this next example, we have the heights array 1, 2, 3, 4, with a total water volume of 2 and a pore index K of 2. Initially, the heights are unchanged, and we have 2 units of water to pour. For the first unit, we begin at position 2. Moving left, we compare heights 1 with heights 2, and see that 2 equals 3. This allows us to move to position 1. However, moving further left isn't possible because heights 0, heights 1. The water is dropped at position 1, increasing its height to 3. The updated heights are 1, 3, 3, 4. Next, for the second unit of water, we start again at position 2. As before, we move left to position 1 since heights 1 equals heights 2. Again, we can't move further left because heights 0, heights 1. Dropping the water at position 1 raises its height to 4. The final heights array for this example is 1, 4, 3, 4. In the third example, we analyze a case where the water has no room to move. The heights array is 3, 3, 3, the volume is 2, and the pore index K is 1. Initially, the heights remain unchanged, and we have 2 units of water to pour. For the first unit, we start at position 1. Here, it's not possible to move left or right because both heights 0, heights 1, and heights 2, heights 1. As a result, the water is dropped at position 1, increasing its height to 4. The updated heights become 3, 4, 3. Finally, we pour the second unit of water. Starting at position 1 again, we find that, as before, it's not possible to move left or right. With no other options, the water is dropped at position 1, raising its height to 5. The final heights array for this example is 3, 5, 3. The time complexity of this solution is primarily determined by the operations performed for each unit of water. First, we have the outer loop that runs for the number of water units, referred to as volume. This means the outer loop iterates volume times. Within each iteration, there are 3 potential movements. The first is the left movement, where the algorithm tries to move from the current position, K, to the left as long as the left neighbor is less than or equal to the current position. In the worst case, this leftward traversal can span the entire length of the array, making it O, n, where n is the length of the heights array. Next, we have the rightward movement, which occurs if moving left is not beneficial or possible. Similar to the left movement, this can take O, n, time in the worst case if the algorithm traverses all the way to the rightmost index. However, the condition POS equals K ensures that this rightward movement only happens if the algorithm has already moved left, avoiding unnecessary redundancy. After attempting the left and right movements, there is a center adjustment step where the algorithm may return towards the original position K. This adjustment can also take O, n, time in the worst case, as it may involve reversing the path traversed earlier. Once the correct position is determined, the water is dropped at that position, which is a simple O1 operation since it only involves incrementing the value in the heights array at a specific index. Now, if we consider the worst-case scenario for a single unit of water, the algorithm may traverse the entire array up to 3 times, once for left, once for right, and once for the center adjustment. This gives a time complexity of O3n, which simplifies to O(n) for each unit of water. Since the outer loop repeats this process for all volume units of water, the overall time complexity becomes O volume asterisk n. The space complexity of this algorithm is straightforward. First, we consider the input and output. The heights array is modified in place, meaning no additional space is used to store the result. The input space is O(n), as it only depends on the size of the heights array. Next, we look at the auxiliary variables used by the algorithm. These include scalar variables like n, POS, and various loop counters. Since these variables do not grow with the input size, they require constant space, or O1. When we combine these factors, the algorithm does not allocate any additional space beyond what is already required for the input. Therefore, the total space complexity of the solution is O1, meaning it uses constant auxiliary space. When comparing this optimized approach with a naive solution, the difference in efficiency becomes clear. A naive approach might involve simulating the entire process by iterating through all possible positions for each drop of water. This would result in a time complexity of O volume asterisk n squared, which is highly inefficient for large inputs. In contrast, the current optimized solution limits the traversal to a single pass for each left, right, and center adjustment, reducing the time complexity to O, volume *n. This is a significant improvement, especially for larger input sizes. It's also worth noting the distinction between the best case and worst case scenarios. In the best case, if all water drops can be poured directly at the initial position K without needing to move left or right, the complexity per drop is O1, leading to an overall complexity of O volume. However, in the worst case, where each water drop requires traversing the entire array to determine its position, the complexity remains O volume *n. To mathematically validate the overall time complexity, we consider the operations performed for each unit of water. Each movement, whether left, right, or center adjustment, is bounded by O(n), which corresponds to the length of the heights array. Since the outer loop iterates volume times, the total number of operations is proportional to the product of volume and n. This leads to the final overall complexity of O volume *n, which aligns with the analysis we've discussed. By focusing on how the algorithm's operations scale with the input size and the number of water units, we can confidently conclude that this is the correct time complexity classification for the solution. When solving the poor water problem, there are a few common mistakes that can trip you up. One of the biggest is misinterpreting the rules of water flow. Remember, water doesn't just fall straight down, it first tries to flow left, then right, and only settles vertically downward if both sides are blocked. Ignoring this order often leads to inaccurate simulations. Another frequent mistake is skipping edge cases. For example, when pouring water at the edges of the terrain, the water cannot flow outward beyond the boundary. Missing this can cause array index errors or unexpected behavior. Lastly, inefficient implementations can be an issue. Using nested loops might seem fine for small inputs, but with larger arrays, say up to 10,000 elements, this results in O(n²) complexity, which is too slow. Optimizing to O(n) is crucial for better performance and scalability. Another mistake to watch out for is not resetting state during iteration. For instance, if you use variables like left and right pointers to track water flow, these need to be reset for each drop of water. Reusing stale values from previous iterations can lead to incorrect results. Similarly, modifying the input elevation array directly is a common pitfall. It might seem convenient, but in real-world scenarios or follow-up questions, you may need the original data intact for multiple simulations or comparisons. Working on a copy of the array avoids unintended side effects and ensures your solution remains robust and reusable. In interviews, it's critical to demonstrate a clear understanding of the water flow rules. Be prepared to articulate the three-step process: flow left, flow right, then settle down. Misunderstanding this is often a red flag. Additionally, showcase your ability to handle large inputs efficiently. While a naive O(n² solution might work for small examples, explaining how to optimize to O(n) demonstrates strong algorithmic skills. Edge cases are also important, so ensure you can discuss how your solution handles scenarios like pouring water at the boundaries or over flat terrain. Finally, be ready for follow-up variations, such as simulating multiple water sources or expanding the problem to a 2D terrain. This demonstrates adaptability and depth in problem solving. If you're looking to build a broader understanding, there are several related problems that can help. LeetCode number 42, Trapping Rainwater, focuses on the total water trapped across a terrain and involves a similar simulation process. LeetCode number 407, Trapping Rainwater 2, extends this concept to 2D grids, adding complexity to the simulation. LeetCode number 1020, Number of Enclaves, also involves simulating flow and handling boundaries, which is conceptually similar to the poor water problem. Lastly, while LeetCode number 17, Letter Combinations of a Phone Number, is more about simulation and backtracking, the problem-solving skills it develops can be highly applicable to dynamic scenarios like this. There are multiple approaches to solving the poor water problem, each with its trade-offs. The brute force approach involves simulating each drop of water by scanning the entire elevation array at every step. While straightforward to implement, this results in O(n²) complexity, making it impractical for large inputs. A more optimized approach uses pointers to track the left and right flow paths, significantly reducing redundant scans and bringing the complexity down to O(n). However, this method requires careful handling of edge cases and pointer logic. For more advanced scenarios, especially in 2D terrains, a heap-based simulation can be used to dynamically track the lowest elevations. While this is more complex to implement, it scales well and is particularly useful for higher dimensional or dynamic problems. Great job! Today, we covered how to solve LeetCode problem number 755, poor water. We summarized the problem, explored the algorithm, and discussed its complexity. Remember, simulation problems are a fantastic way to practice handling edge cases. Thanks for watching, and don't forget to like, share, and subscribe for more helpful content. See you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!